Okay guys, welcome back. So in the last video we talked about the internal resistance of a cell and the electromotive force of a cell and how we can calculate those. So for all these videos we have been talking about concepts in which we found the total electromotive force or the total voltage of the cell within one cell. Now what happens when two or more cells are connected to a circuit? Now say if you want a voltage of 6 volts, but you don't have a battery or dry cell of 6 volts, but you have plenty of batteries of 1.5 volt, a normal Electron uh, cell. So if you want your requirement is 6 volts, but you have only a couple of 1.5 volt batteries. What you do is you can combine 4 1.5 volt batteries to make 6 volts. So that's in a simple setup in which 2 or more batteries are used to make the voltage as you need. So there are setups in which you have to find the total voltage of a series of cells. So excuse me. So in the arrangement of cells also there are two ways. One way is the cells in series and the other way is cells in parallel. So you can, as in resistors, you can arrange these cells either in series or either in parallel. So there are two ways, so I'll be discussing that in this video, cells in series and cells in parallel. So welcome to the topic of arrangement of cells. Arrangement of cells. Right, arrangement of cells. So first of all I will be talking about cells in series. Cells in series. So if you have a number of cells with different electromotive forces like this, one cell to be, I'll take it as E1 and the internal resistance to be R. So I'll take into the internal resistance to be R1, R2 and R3 up to Rn, and the electromotive forces to be E1, E2, E3 up to En. So this will be I1 R1. For another cell it will be I1 R1, E1 R1, E2 R2 for another cell, and for another cell it will be E3 R3. And we can continue this up to the nth cell in which the electromotive force is En and its internal resistance Rn. Right. So we have to find the total electromotive force in this setup. So what actually happens is that the total electromotive force we call is the addition of these. Is the addition of the electromotive forces E2 and then En, or we simply denote it to be sigma from I equals 1 to n Ei, right, Ei. So EQ or E effective to be like this, and R effective to be, now consider this to be a series of resistors, because these are also resistance we are denoting here, to be a series of resistors connected like this. So Req to be R1 plus, R2 plus, likewise up to Rn. So that will be Req or R effective be sigma from I equals 1 to n Ri. Right? So that's about cells in series. Now what happens when cells are in parallel? Cells are in parallel. Right? So I'll take some cells to be in parallel like this. So this is also very similar to the concept of resistors in series and resistors in parallel. So what actually happens is that this. So you can continue this setup of the circuit like this. up to n cells, you can continue. So for the end cell, what happens is that we get something like this. So if the internal resistance, the internal resistance of the electromotive force should be equal, right? Because electromotive forces, I'll take the electromotive forces to be equal and the internal resistance also to be equal, right? So what actually happens is that if you have this one to be E and R, because I'm taking this the electromotive forces and the internal resistance to be equal, because what actually happens is that when you select that, you know that the total voltage across these two ends are the same for all the cells. The total voltage across all these cells are to be the same for all these setups. This is the first setup, second, third, fourth, like that up to n. So here also the E and R. So I'll take the same cells. So to produce the same E, we need the same R. So I'll take it to be R for all cells. Alright. So the total resistance is the same, total electromotive force is the same as we experience for the total voltage. It will be E. Because as in the case of total resistance, or the effective resistance of a series of a lineup or series of resistors in parallel, right? Series of resistors in parallel, the total voltage is the same for all these cells. So the total effective voltage or the total effective electromotive force will be also equal to the value of each of these individual cells. So for this one, for the value of R effective will be 1 upon R, 1 upon R effective, right? 1 upon R effective will be 1 upon R plus 1 upon R, likewise up to 1 upon Rn. So that will be n divided by Rn, 1 upon R effective. So R effective will be Rn divided by n. So to take the R effective, what you have to do is you have to take the value of the now Rn is actually equal to R1, so this is also equal to R by n. So this is also equal to R by n. So we have to take, what you have to do when you have to take the effective resistance is that in a setup in which the cells are parallel, is that you have to divide the internal resistance of one of these cells by the total number of cells. So this is just a simple example in which we can arrange cells. So we can arrange cells like we are arranging the resistors either in series or in parallel. So we can find the total resistance and the total electromotive force. So when it is in series, what actually happens is that the total electromotive force is the addition of the individual electromotive forces, and when it is in parallel, the total electromotive force is equal to either of the cells, because the total electromotive force of each of these cells is equal. So the effective electromotive force will also be equal to the electromotive force experienced by all these cells. So that is E. And for this internal resistance, what actually happens is that the total effective resistance when the cells are in series is the same as when we connect a series of resistors in series. So that the total resistance is the summation of the resistance actually experienced by all these. And when you are taking the cells in parallel, the total effective resistance, as it is in the case of series of resistors connected parallelly, what actually happens is that the total effective resistance will be the ratio of the resistance of one cell to the number of cells. So that's a simple example in which we can arrange the cells in series and cells in parallel. And now what actually happens? When we mix this? So what actually happens when you have a setup like this? What actually happens, right? When we have a setup like this. Now, for the first loop, I will connect a series of cells in series. like this. Series is cells in series, and for the second loop the same. I'll copy paste that. Likewise here, and for the end loop also like that. And what I'll do is I'll connect it through some resistor of resistance R. So this is the important part. This is the important part. If you send a current of I through this, what is the total internal resistance of the cell, and what is the total effective electromotive force on this setup? So what actually happens is that when you have a combination of cells, say you have n cells here, n number of cells in a row, so for all these rows you will have n number of cells, and if you have m rows, so the total number of cells will be m times n, because each row has n types of cell, n number of cells, and there are m rows, so that the total number of cells will be n times m. And the effective resistance will be now for the first row the effective resistance is now I'll take the effective resistance for the first row. Effective resistance EEQ for first row is, now you know from the theory you learned a little while ago, that the effective resistance is the number of cells times the value of E for each individual cell. I'll take the electromotive force of each individual cell to be E, and its resistance to be internal resistance to be R. So for all these cells is the value of E, and the total internal resistance is R. So this is ER, this is ER, this is ER, this is ER. Likewise, this is also ER. Likewise, so for all these cells, the total electromotive force is E, and the total resistance is R. So the total effective electromotive force for the first row is N times E, because the electromotive force per one cell is E. So what actually happens is that you have adapt when you are selecting a series of cells connected in series. What actually happens is that you have to adapt all these E1 plus E2 plus E3 plus E4 plus up to En. So E1 is equal to E2 is equal to E3 is equal to E1 En. So what actually happens is E1 plus E2 plus E3 up to En will be E plus E plus E plus up to N times E. So that will be N times E. So the total effective resistance N times E. And you know that if the total effective resistance of the first row, to be some value, the total effective resistance of this series of cells will also be that value. So the total effective resistance of this series of cells for the series is also N times E. And you know for the total effective internal resistance, that if you have a setup like this, the total effective internal resistance of this setup, Req for the first row is what? Is N times E, right? N times R, because you adapt the resistances R1 plus R2 plus R3. So R1 is equal to R, R2 is equal to R. So R1 plus R2 plus R3, so like that will be R plus R up to N times of R. So the total effective resistance for the first row will be N times R. So the total effective resistance for the whole circuit, internal resistance for the whole circuit, the series is equal to, now if you know that the total effective resistance, here to be some value, and the total effective resistance in the second row to be some value, third row to be some value, what actually happens is that now you know that you have to take the internal resistance of one row and divide it by the number of rows. So it will be NR divided by M. or what actually happens is that this to be Req, n times R will be m times Req series. Right? So that's very simple. So you will get some sums in which two or more cells are connected either in series or either in parallel, or both in series and parallel. So this is the simple setup. So this is the simple equation you can find and you can apply, right? So this you will not forget that, because it's very simple and it's very analogous to the situation in which you find the concepts of the internal, finding the total effective resistance of a circuit when you have three or more resistors that are connected to it. So what actually happens is that you can find the internal resistance, you can find the effective electromotive force, and then you can solve the sum accordingly as you have been given. So that's about the internal resistance of the cells and the internal the electromotive force of cells and the combinations of cells in series and parallel. So in the next video I'll be talking about the Kirchhoff's rules. Kirchhoff's rules are also another set of important rules, so that is also of utmost importance, because Kirchhoff's rules is actually the beginning, as I consider, and as I wish, right, as I take, Kirchhoff's rules is the beginning of current for you, right, beginning of current electricity, because you solve many equations, you solve many problems with Kirchhoff's rules. So Kirchhoff's rules and the Kirchhoff's rules and the effective resistance of a series of cells are the two major important concepts that you will be learning in current electricity. So you have already learned about the total effective resistance of a series of cells, either in series or in parallel or both. So that the first topic is already discussed. So the second topic about Kirchhoff's rules will be discussed in the next video. And thanks for watching this video, and see you then.